It's my pleasure to introduce Greg Malen, who will be speaking for our online network this week. And his talk is on K-collapsibility of random Clique complexes. Thank you, Greg.
Thank you, Henry, for inviting me to talk in this online seminar. You guys about the K-collapsibility of some random Clique complexes. So we're about some homology vanishing theorems as well that show up with these guys. So, it's not. Here we go. So the talk is going to be that first I'm going to tell you guys about the random simplicial model MP. This is some for random simplicial complexes that I'm interested in, and to develop a method for collapsing Clique complexes, and that's going to be a deterministic method actually that works in for complexes. And I'm going to exhibit how to use this method in model XNP when P is small, we call sparse complexes. And I'm going to try to roll this method up into denser complexes, and I'll tell you guys about what happens when we lose the leverage of finiteness, or as it's felt to me often, the loss of innocence in this case. So, and after that, I'm just going to tell you about some more questions and directions that we have. Now, what I do is just talk about some random simplicial complexes, and every example, of course, should be the Erdo-Rini random graph, GNP. So the probability space of graphs on n vertices, or each included independently with probability P. So it isn't be played around with before. It's a pretty great example of this sort of thing, and you can always just imagine yourself spreading points out onto your table, and then up a coin that's weighted with probability P, and flip it. And if it comes up heads, you put your egg in. If it comes up tails, you throw it away, and you get for every edge. And the statements that you want to be making are statements about what happens as n goes off to infinity. Taken from this distribution, we have questions about G having some property A, and then we say G has A, or G is in the set of things that has this property A with probability, if the probability that it has goes to 1, then goes to infinity. It's the kind of question you might ask. One of the best examples, as long as we're talking about GNP, is the connectivity threshold. So if omega be some function of n that goes to infinity arbitrarily slowly, and then G from the distribution GNP hat, high probability G is connected if P greater than or equal to log n plus omega divided n, and disconnected if P hat is less than log n minus omega over n. In this sense, log n over n is really the right threshold to look for connectivity these graphs. And GNP, a graph is really just a one-dimensional simplicial complex, and connectivity is sort of like a homological threshold for H0 or for pi 0. So maybe we're interested in what happens in higher dimensional examples of this. And I'll say there are really two big ways to think about this. One is what's called linear Machulin d-dimensional complex, and then to be something that more closely has to emulate the kind of thresholds you get in GNP in higher dimensional models. And not so much about that, although if you're interested in collapses for that sort of thing, Farber and Kapler have a paper from 2010 where the collapses in the two-dimensional model of that type. But what I want to do is something simpler. I just want to take GNP and build some nice high-dimensional complexes over it. And my favorite way of doing this is to just take the Clique complex of a graph. So the complex, denoted here by x of G, is a maximal simplicial complex with one skeleton, G. And the reason it's called the Clique complex is that every k plus 1 clique, a complete subgraph on k plus 1 vertices, gets filled in k-dimensional space. So this is creating high-dimensional structures, but it's fairly ubiquitous. Anything is going to be, any complex is homotopy equivalent to the Clique complex of some one structure up to some subdivision. This is also known as a flag complex. So if you come from the world of G, you might just be interested in whether things are flag or not, and if something's flag, it's the Clique complex of its one skeleton. And also the Viator-Rips complex, which shows up, of course, a lot in topological data analysis. This is going to be the Clique over some distance graph, depending on your parameter R. So being able to collapse these sorts of structures is going to be something that's fairly useful in different places. And of course, what I want to do is I just want to take this and apply it to GNP. So I'm in XNP, by sort of a horrible abuse of notation here, to be the clique over GNP. And really, this is just the probability space of clique complexes on indices, or each included independently with probability P. I'd be interested in. Some nice things are already known about this. So particularly when P is small, P is equal to n to the negative alpha, for instance, for some fixed alpha, then with ability the dimension is bounded. And that's nice. It gives you a lot of control over what's happening. There's a theorem by Matt Kale in 2014 that says that if I take x from this distribution and I put k greater than or equal to 3 and I fix my alpha in some nice little window, it's 1 over k and 1 over k plus 1, high probability x is rationally homotopy equivalent to a bouquet or a wedge of k-dimensional spheres. And this result, it tells me that all of my rational homology and homotopy actually is just one dimension k. And the way to show this was to show that first k-dimensional homology is non-trivial. Give up. So we found some k-dimensional homology classes. It showed that there are no dimensional homology classes with integer coefficients. And for lower dimensions, was able to show that there's no homology with q coefficients. That's why we have to include the word rational here. I should say, and I'll mention later on, he also requires also some knowledge about the fundamental group of these guys. We'll do that in a bit. Is that in this case, not only dimension bounded, but it's actually going to be either 2k or 2k plus 1 with high probability. So in fact, this rational homology is all concentrated in roughly middle dimension, almost exactly middle dimension. So a nice feature is the kind of thing that shows up in a lot of different places also. But also it leaves open the possibility of torsion in dimensions less than k. If we move the word rational, we have to be worried about this result here. Q, we'd really like that to be something with z coefficients. And I guess we would look at these k-dimensional homology classes and try and see if there's torsion there directly. But what's easier to do is to actually, if I can, my space is conditional, then I have any torsion in top dimension. So we'll look at improving this result to be something about collapse. And summarizing what I was just saying there, if I want to remove the word rational, standard definition from the topological connectivity of a space, and the k-connected if its first k homotopy groups are all vanishing. And if I have that, so if I have a k-1 connected space with a dimensional, equivalent to a potentially trivial bouquet of spheres, but in this case, since we know there's going to be some k-dimensional homology, it would be an actual bouquet of spheres. We could say this. So this means I need to replace, I guess, q coefficients with something about homotopy groups. Homotopy groups tend to be pretty difficult in general, and by the Hurwitz theorem, I know that the first non-homotopy group and homology group are going to be the same dimension if I can also show that I'm simply connected. So it seems like an easier thing to shoot for. On the other hand, I want to replace this statement with collapses to a k-dimensional complex. And it's really the last part that I want to spend most of the time talking about here is the collapsing side of this story. So I guess I should make sure we all know what I mean when I say collapses.
Before you get on collapses, what's known? Like, can you remove rational, or is it conjectured that you can remove rational? Are you looking at just one side, or have you looked at both sides?
We are looking at both sides, and I do have some results. In fact, later on, I'm going to say how these collapses can give us, in some certain cases, that these are going to be bouquets of k-spheres without rational. But the other side of the story, it turns out to be a lot more difficult. So to get this bit about the homology vanishing, it's a more difficult story in general. It's something that we're currently still working on.
But you conjecture it to be true?
I mean, it to be true. In fact, I think Matt Kale has conjectured this to be true for nearly at this point. This has been something he's chasing for a long time here. And that was the motivation behind a lot of this work. Mm-hmm. So a simplicial collapse, this is what I'll be doing, just knocking out pieces of my space. I have a space X which is contained in only one maximal space. Then we can remove all of this that contain that guy sigma through that maximal space tau. And dimension of tau is one more than the dimension of sigma. We call this an elementary collapse, so they're easier to view. But let's look at a picture to show we see what's happening. Vertex is just sort of hanging off there on the edge, and only contained in one edge. So it's not really doing anything to the homology, the homotopy of my space. What I do is I can just punch it in with that maximal space that it's in and get rid of it. And really I can take edge here, that's in one triangle, so I can start punching it in, like punching in a window. It's always fun for me because I like to imagine vast amounts of destruction in these things. But on the end, if I have an edge sitting here, it's only it's in actually two triangles. So it's in the maximal faces, and I do any collapses to it right now. I have a vertex that's in two triangles. I can't do anything about that. Sorry. But on the other vertex, it's up here on the end, and in two edges, but it's only in one triangle. So it's a one maximal face, and I get to punch in along with those edges and get rid of it. And collapse are great because they're homotopy equivalences, so they're to make on my space. And then a space X is K collapsible if it is to a K minus 1 dimensional complex. So K collapsible, I mean all of the K faces and collapse out of my space. That's what I'm going to be doing. But then I want to narrow my focus, and I want to think about links in my complex. So think of a vertex V, simplicial complex X. The set of faces that contain V when I I take the set of faces that contain V, and then I remove V from them. I get the simplicial complex on those faces. An example, this is my complex. I have this vertex V. V is a bunch of edges. And remove V from those edges, I get these vertices. And through triangles, and when I remove V from those triangles, I get these edges around the outside. So V is this around the outside. We can here for a second. It's also the boundary of the star of V, if you're familiar with the star. And then do collapses now to my system. When I look over at the link of V here, that's a really easy thing to deal with. I can take this vertex and collapse it in there. And about what happens if I add V back in, this is really telling me to collapse this edge here along with this triangle. So I take that in my space and then keep moving along and collapsing these triangles by actually doing collapses in the link, which are sort of easier to see. And at the end of the day, what I've done is I've cut all of the triangles that contain V by actually all of the edges that were in its link. And I'm worried, you have to be a little bit careful about exactly how I do this, but what it's telling me is that collapses in the link can be listed to collapses in X. Something that I might want to do if I wanted to get rid of all of my high dimensional faces. I could zoom in on a vertex and then collapse everything above it and then move on. If I want to have some nice way of moving on, I should think about how my dimensional faces are spread out in space. So I need more definitions. Call a simplicial complex pure K-dimensional if it's dimensional, and decimal faces are also K-dimensional. So every face in my space is contained in some K-dimensional, some dimensional face. And it's a really nice thing to see. By example, the one-dimensional complex is just a graph with no isolated vertices. But then I do the Clique complex on space, and I throw in all of these triangles. I'm not really dimensional anymore because I have these edges sitting here, and they're not contained in any triangles. And then what I want to do is I just kind of want to ignore them. Right? I want to think about the pure two-dimensional subcomplex sitting here, and that's what I'm interested in. The last definition that I need is I want it when things are strongly connected. So pure K-dimensional complex, strongly connected, it can walk across faces for crossing over dimension 1 intersections. So if I have a bunch of triangles sitting here, this is strongly connected because from this guy to the other guy, I just have to walk across these edges. If I add in some more triangles, I'm going to be strongly connected. But add in a piece like this, I'm no longer strongly connected because in order to get from the left side to the right side, I have to cross over this vertex. And that's just 0. So things are kind of bothersome, maybe simpler than it looks. Now I just want to think about these two strongly connected components that I have sitting here. And I divide my space up into sort of these components and get faces here. The remark, what makes this nice in particular is that if I have a face that has dimension greater than or equal to k, its skeleton, all of its faces of dimension at most k, is strongly connected. So this guy is then supported on some unique maximal strongly connected component of my text. Make sense? Okay. So now collapsing the theorem in all of its glory. If this is a finite Clique complex, then order is that every one of these pure plus one-dimensional strongly connected subcomplexes has a degree at most k plus 1. And so what we're saying is if every sort of sufficiently nice subcomplex has a vertex of small enough degree, then I use those vertices to collapse out all my high-dimensional faces. And it's by induction, really. So is 0, being null is the same thing as having no isolated vertices, and strong connected is the same thing as being connected. So what this degree condition tells me is that every connected subgraph for a vertex of degree 1, and that's not having any cycles. So that's this then becomes equivalent to collapsing a force down to a set of vertices, which assuredly do. I just want to induct on k. So now we're thinking about higher dimensional things, but if I space up into k plus 1 dimensional strongly connected subcomplexes, it has finitely many of those because my space is assumed to be finite, and then is assumed to have some vertex, more than one, but at least some of degree less than or equal to 2k plus 1. And to start, let me talking about pure k plus 1 dimensional complexes. I don't have any of the faces of higher dimension yet, so I need to throw them back in. Of course, I do that is just by forming a complex over each subcomplex. The set of complexes I get now covers and partitions all faces of dimension at least k plus 1. And I have to, because they have some intersection, right? I can't collapse, yeah.
Sorry, Greg, can I get you to back up just a little bit?
Oh, absolutely.
You have so go to the k equals 0 case, you have a connected subgraph that has a leaf.
Every subgraph has a leaf.
Like if you have a connected subgraph with leaf, I can imagine one that does have a cycle.
Right. This word every is really important for exactly that reason. And the surprising thing to me actually is that this seems like a really strong condition to ask for in general. Because saying every one of these subcomplexes like this has to have this condition. It's surprising a priori that we actually this for random complexes. So that via this model XNP, it's sort of going to tell us that a generic Clique complex actually does have this really strong condition, which it's surprising when I first realized this. Yeah. Right, we were forming these Clique complexes here. Intersection, right? If I look back to the last picture I had on the page, we had the vertex they intersected in. So I have a little bit about that, but the nice thing is that this doesn't add any edges. So internal vertex degrees are preserved, and I didn't destroy this vertex condition that I asked for. As on, now what I want to do is I want to pick some, let's say S1, collapse all of my faces in a particular subcomplex which contains a vertex that we know has small degree. And doing that, collapsing all of those high-dimensional faces is going to contain faces in the link. And instead of collapse everything in S1, I can go into the link on a particular vertex and choose all of its faces that have dimension greater than or equal to k. Right? Because I add a dimension to every one of those faces when I add V1. And I really need to think about then is what is the link of V1 in S1 bar? Well, complex. Anytime I have a clique complex, the link of vertex is also a clique complex because connected in S1 bar, say, is going to be connected when I look up at the link to 2k plus 1 vertices. So either I'm the full clique graph, if the link is actually the two-dimensional or 2k dimensional simplex, excuse me. And to imagine how you can collapse this. In fact, you can sort of pick, I have it on the slide, but you can pick a cone vertex and collapse everything to that vertex. But certainly this can be done. And I guess the option is the proper subgraph. So if my proper subgraph of the complete graph, the complete graph is 2k regular. Every vertex has degree 2k. So if any edge, then every subcomplex that I could possibly build is going to have some vertex of degree at most 2k minus 1. That is exactly the same degree need if we were to do this theorem and k collapsible. So we have, in this case, we can do the collapses by induction. Okay? And then what do we have left over? So I've called everything that contained V1, and what remains in S1 bar minus V1, minus all of the faces that contain V1. And it's still a clique complex, because again, everything that, the edges that I removed maybe were edges containing V1, if I was removing edges. And it might not be strongly connected anymore. So I have to split up into a bunch of different pieces, but complex, and I'm going to satisfy the degree condition, not because of heredity. Any complex of S1 bar was going to be a subcomplex of X. So dimensional and strongly connected, then I would have the degree condition. And then if X is finite, I can just iterate this process until it terminates. That's basically the idea. Anyway.
So that if it breaks up into pieces, then you just hand each piece separately.
That's right. That's right.
Okay.
Yeah. So bar minus V now breaks up into his components. And really, you know, in a more complete proof of this, it's really a double induction number of vertices now in one of these components. If I can always peel off one vertex at a time, is what's happening.
Thanks.
All right, so that's the deterministic method for collapsing clique complexes if I know I have that condition. And piece here, when we say what happens if it is the complete graph, this is where we needed it to be a clique complex. That was really important because I link in, you know, I maybe could have ended up with the boundary of a tetrahedron, and if I didn't know that was filled in, I would have a problem. I wouldn't be able to collapse that. So that's really a place where we're using the clique complex. Otherwise, I can still do lists of collapses in my link to collapses in my complex. That still sort of works in general, if you're okay. As I explain why is this what we were even looking for in the first place? So here's some about non-trivial homology classes that are useful. If I'm complex, maybe I think a list, but if minimal representative of a non-trivial class, then it is purely dimensional and strongly connected complex of X. So that's when to ask for exactly this sort of subcomplex in the first place. And the Clique complex, then V has internal degree at least 2k. Not obvious. This is, I think, well-known fact, although I've seen proofs of it by both Michel and Kill as writing out results. But the intuition for it is that the smallest possible Clique complex that I can have that's non-trivial k-dimensional homology is the conditional cross polytope, or octahedral k-sphere. If you're familiar with this, you should really be thinking of the octahedron, or like E square. That's sort of what we're talking about. And this is 2k plus 2 vertices, exactly 2k regular. And now here are those two conditions that we were just asking for. And if I have those two, or rather if I don't have that degree condition satisfied, already I could have said that this guy was going to have no homology above dimension k. And in fact, what Kim did to show that there was vanishing homology above dimension k in the first place, he used exactly the conditions to make in the sparse case when you had homology. And the statement of the theorem is as follows: I take x distributed from xnp, my parameter k at least 0, and then I have some arbitrarily small epsilon, then are equal to n to the minus 1 over 1 k minus epsilon. So the interval that we had alpha in between before, this just says that my alpha is sort of just above 1 over 1 plus k. Then we know exactly that xnp satisfies this degree condition for its nice subcomplexes. I'm going to do the details of this proof in a little bit because the details are interesting. They work for p in this small range, and what I have to do is try to apply them to Denver probabilities, what happens when p is 1/2, something like that. But basically, what he did was he showed that there are no strongly connected components on more finite number of vertices. So I have some fixed big N that depends on this parameter epsilon that I chose, and below that, there aren't any subcomplexes with high degree, with an degree at least 2k plus 2. Have high minimal degree or have strongly connected, but you can't have them both in XNP. And once you know this, you can now add in this deterministic collapse theorem and say that if x distributed from XNP, I fix all parameters, then I know that with high probability x is k plus 1 collapsible. So it's k-dimensional complex. So of trying to find these collapses in the first place is we wanted to find these collapses in XNP. And one remark is that certainly if k is equal to 0, this was well known beforehand, if p is much less than 1 over n, then the GNP is a forest. It doesn't contain any cycles and access to a subset of the vertices. Of course, that we want to know, as Henry asked earlier, is what does this tell us about bouquets of spheres? That's sort of the interesting part of this game. And now fix k greater than or equal to 0, and I fix my alpha interval. And we know that in the k equals 0 case, that we're going to get a bouquet of 0 spheres, if you like. Sort of an idea about bouquets, but it makes sense. And then the new result that we have is that if alpha greater than 1/2, I'm collapsing down to a one-dimensional structure. So if one and I'm connected, which this is beyond the connectivity threshold, that's equivalent to a bouquet of 1 spheres. Here in this range for alpha between 1/2 and 1, we have the fact that with high probability x is homotopy equivalent to a bouquet of 1 sphere. So nice. And the question then, can we go further? Well, this it's in fact not going to be true for k equals 2. In this, between 1/2 and 1/3, xn non-trivial pi 1, so it's not simply connected even, so it's definitely a bouquet of 2 spheres. And Babson showed this originally in 2012. It was also independently, I believe, Costa Farber and Horak a year or two ago in different work. But for k greater than 2, what can we say? And certainly at the moment, this is still open, although we do know that pi1 is going to be 0. So we show that this is, for alpha less than 1/3, these guys are simply connected with high probability. On the other hand, we don't really know about this integer g less than dimension k. And now it's part of ongoing work with Chris Fowler and Chris Hoffman at the University of Washington and Matt Kale at Ohio State. That sort of sits. But one, the next is what happens as I try to increase my probability parameter. What do these start to look like when I start to get into denser regimes? And in order to understand that, I really need to look at what happened with this proof that my NP did satisfy my degree condition in the sparse regime. So, again, pieces were one to show that there were strongly connected components on too many vertices. And the way we do this is first we need to get a lower bound on the number of edges. About how we were building strongly connected spaces before, I kind of added on one triangle at a time. And it's theorem, maybe it's obvious it's something that does need proving, but I can always build a strongly connected complex like that, sort of one triangle at a time, one with all of the edges it comes with. Off with just a k+1 dimensional space, like the vertices and edges I have, well, like a vertex, then it comes with its k+1 edges that I'm using to connect it to whatever there. And I keep going in this fashion, as these and k+1 edges. But I think there's a distinct possibility here, and that's maybe I have this new vertex, but it also to some other vertex that I think about. And so I should be adding in this edge in this space too, and it changes my equal sign here to a greater than. But that'd be a good enough bound to have to begin with to start doing some patient arguments, some first-order arguments, to try to, we can't have any of these subcomplexes. And the works is I say, well, let's strongly connected complex on exactly k+2+n vertices. Okay? Then its action, the expected number of these hanging around in X, just from XNP, choose V vertices, and I don't order, right? Because I don't know which ones are connected to which ones H yet. I have to order them first. And then I need, for each edge, I need to multiply by P. And no doubt here, one reason why it's less than or equal to should be dividing by the symmetries of H. But if symmetries, that just makes this even smaller. So I'm fine just saying this is less than or equal to this. And start trying to simplify this expression. This piece here, n choose V times V factorial is equal to n to the V. So sometimes you just work with n to the V, P to the E. And to write down what was happening, well, k+2+n, then I know the number of edges I have is at least this down here. And we've constructed this in just the right way, so this goes to 0 and goes to infinity. We plug in as a bound this n to the -1 over 1 plus k minus epsilon.
Greg, you're counting the expected number of maximal strongly connected components?
I'm just saying, just that some fixed H, some strongly connected complex doesn't have maximal. And so what you should worry about is I'm telling you about something that happens at k+2+n, but if something that's bigger, then it means one of the guys on the k+2+n vertices as a subcomplex.
So you're counting the expected number of strongly connected complexes with exactly that many vertices.
Right. And in fact, first what I'm doing is I'm just fixing one of them. Right?
Yeah.
And if I have expectation going to 0, then because of inequality, I have the probability of the any going to 0. But now, of course, there are only finite many such H possible on a finite number of vertices. So I am adding up a finite number of things that are all going to 0, and the probability there's any such H in X going to 0. Right? That's the game. Again, because any big complex would contain one of these as a subcomplex, now I can't see any strongly connected subcomplexes on more than this many vertices. And we're going to aim for the other half of the story, that there are no complex than this many vertices with a vertex of degree no this many vertices with high minimal degree. So fix one of them again. Let's fix H to be some graph degree at least 2k plus 2 and see what happens. So the that I have is always the sum of all of my vertex degrees, and I can bound that now by 2k plus 2. So when I divide by 2, I get k plus 1 times v. Now if I look at the expected number of h, again we have the same setup to start, but e becomes k times v. And if I set p to be, well that's exactly what I would want here to get n to the minus epsilon, and of course going to 0. And all the ones I have on the vertices, so many on at most k plus 2 plus n vertices. So again, if there are any, it goes to 0. And that's really nice. But if I do this for complexes, finitely, that keeps getting thrown around should really be upsetting to me. Because what happens is as soon as I make p bigger, the dimension of my space is going to start to become unbounded. So for the dense regime, well, pure formula works when p is as something like 1/2. This is sort of the bound where I can apply this formula directly, and if p equals n to the minus alpha, when I plug in here, I exactly get back my 2k plus 1 that I had before. Now what I want to do is I want to make p just a little bit bigger. So what about p equal to log n to minus alpha? So just a little bit bigger. Well, then is that I see when I plug into this formula, my dimension is going off to infinity at some rate. So if I had this k plus 2 plus n, well, dimension is going to be going off to infinity, so I'm not going to have the leverage of finiteness here. Say what we can say about these guys. So the thing I would want to know is we're trying to collapse 2, right? And in sparse regime, we were trying to collapse down to half the dimension, so that k alpha be roughly half what I expect the dimension to be here. I'll tell you is there is some non-trivial homology in these guys right around half dimension. So alpha, and I take from this distribution, then with validity I have non-trivial homology for all integers that are in this little interval here. And the way this is done, again, it's just finding k-dimensional cross polytopes that have one face which is maximal in X. And there's a lot of horrible second moment calculations that go along with doing that. But I'm looking for things like squares that have an edge that's not a triangle, right? Because I'm definitely bounding some cycle. The fascinating thing to me about, in this particular case, this interval that I've got, though, is that I have finite length. So alpha is going off to infinity. With really, I've only found a finite number of dimensions with non-trivial homology. And if alpha is greater than 1/2, then I greater than 2. So this is nice because I'm not going to get a wedge of spheres, but I'm minus 2 connected and k-dimensional. So in k-1 connected, now there are maybe 2 dimensions that I have to worry about. Then it'll be equivalent to a wedge of k spheres, k-1 spheres, and some more spaces, which are something that have torsion in dimension k-1. This sort of tells me that if I could do all this other stuff, if I could collapse down and then get rid of all my integer homology in lower dimensions, then I would fully characterize these spaces, the homotopy equivalence. Super cool. So what we can do, well, if I attempt to do this, again, I can't use the same game that I had before. So maybe naively what I want to do is just count up all of the complexes that are as big as a cross polytope and have minimal degree. Maybe that's starting on, and just generally, this looks something like this. I sum the number of vertices I have to some bound, which I'm going to talk about in a minute. And then I take the number of edges. Well, I know I have to have at least k plus 1 times v. and that up to all of the edges. And now I choose V, I have to choose my V vertices. Here I choose my E edges, and here P to D, and then these are non-edges, minus P. And this is usually not useful. If P is really small, this here is usually 1 at a very fast rate. If P is a constant, if P is something like 1/2, I could imagine that being useful. This equation that I've left off this bound here. What am I number of vertices up to? Is there somewhere I can stop? And the point here is that if I knew an upper bound, so for instance, we could bound the number of vertices in a strongly connected component by some constant times log n, then it does go to 0 when p log n to the minus alpha. But upper bound is not so straightforward. It's sort of like it's very similar to a Watson branching process. You can show in GNP, the critical window, you have connected components that have size that are bounded by a constant times log n. But is that new faces can be added on as events aren't just k plus 1, and it's difficult to keep track of all of the different ways that I add on a new face to my system. So and it's not really clear how to do that. Something that I think is promising, and it looks like it can be done, but I haven't been able to make it work yet. So that's an interesting place for a minute there. But maybe what we can do is we can just settle for some homology theorems. Maybe I can at least show that there's not homology there. The way that I want to do this, well, in both and the dense regimes, I can sort of combine them now into what looks like this. So if I have alpha greater than or equal to 0, and some constant c between 0 and 1, I can tell you there is no integer homology of this function here, 4/3 log n over log 1 over p. And you should be thinking is that that's about 2/3 of the expected dimension. Of the expected dimension, there's no non-trivial homology with inner coefficients. And what this is done is to show that the expectation of some subgraph necessary for homology goes to 0, kind of like before. And key insight here is that if I have a minimal representative, then k minus 1 face is in least 2 cases. That's what we call those. And the picture is pretty forward. I'm calling this TK just to give it a name. Well, additional face, then I have k minus 1 dimensional faces in blue here that need to be closed up. So X of edges to close those up, right? And I have to do a one for each of these edges because, I mean, imagine in 2 dimensions, if I connected this vertex here to this up here, I would have created a tetrahedron and it's complex, so that gets filled in. As 2k plus 2 vertices, and it has k times k plus 1 edges, because each vertex I'm adding k1 edges along with it. And some expectation calculation. Now the other thing here is that I have, again, this sort of idea that, well, c contained in tk plus 1, so in the theorem I just showed you, I just have to show it right at this boundary point. And this is straightforward in terms of an expectation calculation. So you choose your first k plus 1 vertices, choose 1 more vertices, and choose which edge you want to close up with each vertex. And when I say that, I mean something like an n to the 2k plus 1 coming, and the term that's left over, that's basically 1 over k plus 1 factorial hanging around. But of course, this part over here is exactly so that I have the same number of positive n and negative n hanging around. So if this is just 1, then this is going to throw pretty quickly. He is above this threshold. And that's that vanishing theorem, which is good. Again, it's a nice but it's not satisfying. I really collapse these if I can. I kind of think that I can. So let's talk about some of the future directions for this. One question I have for a group of people who do a lot more computation than I do, I don't do any computation really at all right now, is would this collapsing method be something that could be algorithmized in say? Because you're just always looking for a vertex of small enough degree and using two collapses. I have no idea. Maybe it would be a very inefficient way of doing it. I really have no idea. Again, I want to improve these bounds so that some collapses in this sort of just above the classic sparse regime. And maybe if I can't do that, I'd be happy improve homology vanishing bound. So we have this picture on this last page, and I still have all of these edges now. I have more edges that are not closed. So I'm able to keep on adding faces to it. But if I did these two edges here, vertices here, and these two vertices here, and these like sort of a circle around the outside, I would have the boundary of the octahedral sphere or cross polytope. And I know they can support homology. So already be a little hard to start pushing on this argument without some horrible counting going on, which seems to be the and hence my loss of innocence here. So the big thing I want to be able to do is I want to show that all non-trivial homology is concentrated somewhere around middle dimension, even in increases. And actually, I'm going to hit some threshold at which my space is contractible with high probability. If too many edges, then every connector and I filled in too many faces. It's definitely going to be contractible. And I like to be able to say that this homology persists, which is a data word to use around TDNO, but sort of persists up to this threshold. And I would, of course, like to find that threshold. I can do a quick upper bound on it, at least. I have P is greater than or equal to 1 minus omega over n. Well, this conic threshold for a graph in the sparse regime, basically what this upper says is that in my element, I have x that's isolated with probability, and then my actual x and p now, I have a vertex that's connected to everything else. And if the Clique complex is contractible. So enough, and it's an upper bound, but actually if I had to guess, I would guess it's more than 1 minus n to the negative 1/2. And this threshold here comes out of some results from doing some bad second moment calculations, and then 1 or 2 other properties of G and P. Where all of this is going. And again, I haven't told you anything about the story of the low dimensional side of this. And that's something that's still in the works and is sort of harder to discuss. But thank you.
Thank you, Craig. So, Greg? Just a clarification question. If you went to slide 2021, you're talking about vanishing of homology.
Yeah.
Okay. So not right.
Right. So all I'm saying here is that above this threshold, there's no integer homology. So I don't know if collapses or not, but nothing interesting is happening out there in terms of the homology of the space. I sort of feel like if we could get some better bounds on these strongly connected complexes that sort of against things going off to infinity, then we would be able to collapse them, at least for P a constant. Maybe P something that's going 1 very slowly, but for P 1/2, it sort of feels like these should collapse down to half the dimension.
Right.
So question.
Yeah.
For this kind of nice range of values of P, you have that your space is homotopy equivalent to a bouquet of spheres.
Mm-hmm.
Have you thought about thinking of P as being a kind of parameter rather than a constant, and whether or not any of these spheres persist through part of this range?
Right. I really hadn't actually asked that question before, and I think I think it's definitely worth looking into. It'd be really interesting to talk about, because that's sort of what I'm looking at. What happens really as P increases, and again, I use the word persists, which makes that I should be doing something with persistent homology there, actually. I think it would be interesting to look into.
This would be interesting. Such results.
Yeah, I mean, I can tell you in the low dimension, so a sparse case where you really do have this, maybe I can find just something just that interval with alpha here. Right. So what happens right around this 1 over k1 and 1 over k is you actually do get some combination. Like if alpha was equal to 1 over k plus 1, you do get both spheres and k plus 1 spheres. You sort of see the homology rolling up in that way as it crosses this boundary. By this for being k minus 2 connect k dimensional, we know there might also be some more spaces. And I think it does beg the question of, is what's happening is now you're sort of attaching some higher dimensional guy onto one of your smaller dimensional spheres, and for a while it's up, and then resolves and becomes a bigger. I think certainly be what's happening. I don't know.
Could you say whether or not any of these translate to kind of other rules of simplicial complexes, like maybe random geometric simplexes?
So again, I think since the passing is just something about Clique complexes in general, condition is totally deterministic. Have this degree in a random geometric complex. If you made it a Clique complex, then I think you might be able to apply it, and that's something where I have time thinking about how the metric plays into it. But I would love to talk with people about trying to find some way of implementing that collapsing system in other methods.
Thanks.
Greg, I have a question. If you could slide about more cases, that might be helpful.
Yeah.
I don't know that.
I have no. It must be after this.
Okay. So, the more cases that appear, and you're looking at some regime where you have non-trivial homology in adjacent dimensions.
Right.
Known that you never have homology in more than 2 adjacent dimensions.
So this is really an existence of non-trivial homology classes theorem. It doesn't tell me that I don't have homology elsewhere. What it does tell me is that I don't have really simple homology elsewhere. These cross polytopes are looking for spheres in some other social complex. They're the simplest thing you could look for. And usually what happens in most random models is that you either really, really big homology classes or really small ones. And so there are no cross polytopes, and there are no cross polytopes greater than this threshold at all with maximal faces like this. So it implies that we should be thinking that there is no homology above that range at least.
Got it. Oh, top of your head, do you know of any examples where, say, non-trivial homology in some random model comes not from cross polytopes, the small spheres, or the boundary of a simplex in a non-Clique complex model, but from these larger?
Well, maybe the right thing to think about there is some of these hitting time models. So you know what happens when you add in faces or edges one at a time. This is something where in the Malen models, for example, if you add in one face at a time, you see these huge bursts of torsion that appear and disappear very quickly. So they only last for a couple of faces. And so it was, probably what's being, we think, the conjecture right now is that it's just something that gets twisted up on like a tetrahedron, but it goes out into the space and then comes back in some horrible way. And so that's something where something bad happens. But for the most part, when you're looking at the hitting time type models, you usually don't have that, as far as I know.
Greg. Well, then the time for a fantastic talk.
Thanks, Greg.